Good afternoon, students. Today we will take another example of a system of bosons, which is vibrations of a solid at low temperatures. And I am going to take low temperatures. So, how is this a system of phonons? This is because we can think of a solid at low temperature as a network of ions, and this is basically to simplify the whole picture. I am showing ions in one dimension. So, let us say the interaction is modeled in terms of a Hookean spring and whose spring constant is given by the second derivative of the interaction energy. We will discuss all that, but just to illustrate the point, I am showing ions here in one dimension. So, at low temperature these ions would be sitting at equilibrium, mechanical equilibrium, which would be like the potential energy minimum of their nearest neighbors. So, they are sitting at mechanical equilibrium at t tending to 0 or t equal to 0. Now, suppose I lift the temperature from 0 to some non-zero values. So, at low but non-zero temperatures, I will take some low temperatures, you expect these ions to undergo some displacement. Okay. So, there are displacements from mean positions, which means you can think of an ion that has displaced in by some in one dimension. An ion could have been displaced by some displacement, let us call it as dx, and in 3 dimensions you would expect this displacement to be a vector having 3 components. Okay. So, for n ions in 3 dimensions, you expect that the total potential energy is now a function of these displacements from the origin, okay, because the interaction has been taken to be sufficiently harmonic in nature. So, I can write down the potential energy at non-zero temperatures. So, we can write down the potential energy as some potential energy that was at t equal to 0, and now you are going to expand it in powers of the displacement. So, u0 is the leading term, which was the potential energy at the equilibrium, and now you can expand it. So, the leading term of course would be you have to take the derivative of the potential, and keep in mind that there are n particles in the system, and you have to accommodate that each particle has 3 degrees of freedom. So, this derivative, this gradient of the potential energy will be running over all particles, and for each particle you will run over all components. So, let me just write it in a way that makes the things much more clear. So, I am going to sum over all particles. Okay. So, Ri such that I belongs to n, and I am going to sum over all alpha which belongs to 1 2 3, okay. And this is nothing but the leading term, fine. So, it has du by dx of first particle, du by dy first particle, du by dz of second particle, and so on and so forth. Let us write down one more term which is due to the second order displacement. So, what we have taken is nothing but the first order displacement. So, because this is a Taylor expansion, I have to multiply it by the displacement. Okay. So, this completes the first order term. Then I am going to write down the second order term, and due to the limitations of the space I am going to write the second order term below this. So, the second order term is summation over all ij's and alpha betas, okay, of the second derivative So, by taking all combinations of I alpha and j beta, you are taking second derivatives of all types. So, there will be d square u by dx square for first particles, there could be d square u by dx1, dx2, and so on and so forth. So, basically all possible second order derivatives have to be taken here. Naturally, I have to this is nothing but the derivative. I have to take the order of the displacements, which is quadratic in displacement. So, you can say that the strength of the displacement is quadratic here, and then naturally the higher order terms are being dropped here because they are of the order dr cube. Okay. We are considering displacements that are very close to 0 or displacements that keep us very close to the mechanical equilibrium. So, this is basically the low temperature approximation that my terms of the order 3 are going to be 0. Not only that, if you look at the first term, first subleading term here, which is proportional to the derivative of the gradient of the potential energy, this will also be 0 because again we are at low temperatures, which means that we are close to mechanical equilibrium, and if that is the case, then this term negative gradient of this term, which is gradient of potential energy, has to be seen with negative of the force. Okay. So, the term that I have taken to 0 is due to the fact that I am close to mechanical equilibrium. So, this del u by del Ri, which is the gradient of the potential energy, it is nothing but negative of the force acting on the ith ion and the alpha component of it. Okay. So, as you can see, I have taken a gradient on the of the potential energy with respect to the ith particle. I have taken up the alpha component of it. So, it is the negative of the force acting on the ith particle and the alpha component of it, and that has to be 0 because we are close to mechanical equilibrium. So, all first order derivatives will be 0, and we have taken the higher order derivatives to 0 because they are anyway negligible. So, our potential energy is basically now nothing but some reference which is arbitrary. The energy is a state function, its reference is arbitrary. All you measure in any process is the change in energy. So, u naught does not pose any issue to me, but this is actually added to a more meaningful and interesting term, which is the Hessian. So, I have to sum over all I and j's, okay, and alpha and beta, and the better way to write this is not Ri Rj, but just Ij, because we are summing over I and j. So, let me just write it as I comma j and alpha beta, and the same here I am going to just write this as a summation over I alpha. Okay. So, here I belongs to 1 to n and alpha belongs to 1 to 3, this belongs from 1 to n. Okay. So, now we know that the potential energy is now reduced to a reference u naught plus a second derivative of potential energy with respect to the coordinates. Okay. And this second derivative of potential energy, if you see, can be written as some kind of a matrix element, because there are 4 indices here, and you can take each direction to be a combination of 2 indices. So, eventually this will be a matrix of if you take n particles in 3 dimensions, then this turns out to be a matrix of size 3 n by 3 n. So, I can write this u naught as this I can write down this second derivative as a matrix of rank 2 or tensor of rank 2, and I can write this as some H, and H here is basically nothing but a Hessian matrix. So, I am going to write it as some I j alpha beta d r I and d r j comma beta. So, here the matrix of second derivatives is basically a it is also called as a Hessian matrix. And if you take n particles in 3 dimensions, then this matrix has a size of 3 n by 3 n. Okay. So, you can write down this matrix of second derivatives in the form of a array or a 2 dimensional matrix, and if you look at the form of this matrix, it does not matter if I change the location of alpha and beta, because this matrix is symmetric in its indices. So, being symmetric in nature, okay, I can it is diagonalizable, which means there exists a unitary matrix U that can readily diagonalize it. So, if I construct a unitary matrix U, then U A U transpose, okay, can diagonalize this into a matrix of only diagonal values. So, this matrix would be nothing but a matrix of all the eigenvalues, which are nothing but your normal modes. Okay. So, here these lambda i's are nothing but normal modes, of vibration. So, this is a matrix of size 3n by 3n. When you diagonalize it, you will get 3n eigenvalues, which are nothing but the modes of vibration of a solid. So, this would be like there are n particles in the solid and this is a 3-dimensional system. So, if you ask the following question that how many different frequencies one has to consider, then there are precisely 3n frequencies, one for each direction and n for each particle, total 3n. So, these are 3n fundamental I would say 3n fundamental frequencies of the oscillator. Okay. So, I can now expect that the system has 3n oscillators, okay, and we can now think of the Hamiltonian due to these 3n oscillators. Okay. So, our system has each particle has now oscillations in 3 directions. So, it is like there are 3 oscillators for each particle and now we have n particles, meaning that the system can be represented by 3n oscillators, and these oscillators can be attributed some energy, which is our Hamiltonian. Okay. So, we can write down the Hamiltonian in the form of the summation over all the oscillators, where alpha will go from 1 to 3n, and we will write down the energy of this oscillator as some excitation plus 1/2 h cut omega. Okay. So, here the half h cut omega is the 0 point energy of the oscillator, and this is 0 point energy of the alpha oscillator. Okay. Now, what is n alpha here? Now, each oscillator can be in a state of excitation. Okay. So, n alpha represents the state of excitation of the alpha oscillator. In some sense, n alpha tells us basically the occupation number of the alpha oscillator. Okay. So, how many phonons are there in the in how many quantum of energy, which is the number of phonons in that energy level alpha or in that oscillator. So, n alpha represents in some sense the excitation of the alpha oscillator, and omega alpha in some sense tells us the vibrational frequency of that oscillator, fundamental frequency of that oscillator.
Frequencies are not necessarily same.
Yeah. So, we have, for this reason in this discussions we allow different frequencies for each oscillator, and n alpha simply represents in some sense the excitation of an oscillator having a fundamental frequency omega alpha, right. So, now you can, the fact that we are dealing with a system of bosons, there is no upper limit on the maximum number of bosons I can accommodate in a level. So, n alpha here in principle can be 0 to infinity. What this means is that there could be infinite number of phonons up to sitting in any oscillating mode, okay. So, or any oscillator, which would simply make the total energy of the alpha oscillator. Now, there are 3n oscillators. So, you simply take what is the energy of each oscillator and sum it over all oscillators, that will give you the total Hamiltonian in the system. So, now I can write down the I can imagine or a microstate of my system. Now, this is where the question of what is n alpha becomes more clear. So, the microstate here is nothing but the set of these excitations, you know, where this I belongs to. So, what is the, suppose you take the ith oscillator you know, to be in excitation n1, jth oscillator to be in excitation nj, these are numbers. So, different set of numbers for each oscillator is nothing but the microstate of a system. So, if you specify one microstate as n1, n2 all the way to nn, some specified values, this is one microstate. You can take another microstate as n1 bar, n2 bar all the way to nn bar, this is another microstate. The set of excitations of each oscillator is one microstate for you. This way you can construct a large number of microstates for your system.
The sum of your small n's will be total n.
No, that is not n. Ni's cannot sum up to a conserved quantity because you can have any number of bosons. You have only 3n oscillators. Okay, so here I think I should take the last object to 3n or dn. Here the particle number is not conserved, we do not have a, these are not real particles. Okay. There is no restriction here that there is no restriction here. If your question is that if I sum over all i's going from 1 to 3n, n i's, this will be 3n. There is no restriction like this. First of all, n i's are excitations of ith oscillator. It could be in any state. In fact, I will take n i's in the following discussion from 0 to infinity. It could be in any excited state. Okay, so we do not have to conserve the number of these virtual bosons, in this case the phonons, to something. Okay, their number is not conserved, and so this number does not is not fixed. Okay. So, how would we write down the partition function? So, the partition function can be written as summation over all microstates. So, I am going to sum over all possible excitations. So, the first oscillator may have an excitation n1, second oscillator may have an excitation n2, third oscillator may have an excitation n3, n1, n2, n3s are some values. The sum of these ni's is not conserved, okay, you do not have the conservation here. So, then we can simply say that our partition function here is a summation over all the microstates of the Boltzmann factor, that is written as e raised to minus beta, and the Hamiltonian. Now, our Hamiltonian itself is a function of all the excitations, but the way in which it depends on the excitations is nice. So, it is written as summation over all the excitations e to the power minus beta, and our Hamiltonian is nothing but we have to now add up the energy of all oscillators. So, the energy of each oscillator, Hamiltonian is the total energy of 3n oscillators. So, the energy each of oscillator is n alpha plus 1 by 2 h cut omega alpha. This is one oscillator. You sum over all alphas, there are 3n oscillators. Now, the n alphas that you take here in the Hamiltonian correspond to the microstate that you have taken here. Okay. So, you keep changing that microstate, compute the total energy and compute the Boltzmann factor. That is how you will compute this sum. Okay. So, then this would simply become, if you think of it this way, it is nothing but I can write it as summation over all possible microstates, okay, e to the power minus beta. I can take it as n1 plus half h cut omega 1 into e raised to minus beta n2 plus half h cut omega 1 2 all the way to e raised to minus beta n 3n plus 1 half into h cut omega 3n. Fine. So, this is like I can take this as a product and I will take this product outside. So, this would be a product of j going from 1 to 3n. So, I am going to write it as yeah, since I have taken this product on over all the exponents outside. So, the inside is just summation over 1 n j, that will go from 0 to infinity e raised to minus beta n j plus half h cut omega j. Okay. So, the 3n products are outside. For each product you take n j going from 0 to infinity, and then you can think of it this way. That the I can do it this way, that the summation does not operate on omega j, it only operates on n j. So, what I will do is I will take the omega j is operated on only by the product. So, I can take e to the power minus beta h cut omega j outside, and I will say that the summation operates only on n j's. Okay, the summation variable is n j only, and this is e to the power minus beta n j h cut omega j. Okay. So, for the summation the omega j is a constant here. Correct. So, there should be a omega j by 2. Fine. Okay. So, this summation is only on the n j, not on omega j, for which is constant inside the summation. So, I can write it as product over all 3n modes e to the power minus beta h cut omega j by 2, and this would be nothing but if you do the summation, write down the first few terms. So, for n j equal to 0 you get 1, then for n j equal to 1 you get minus you got e to the power minus beta h cut omega j plus e to the power minus 2 beta h cut omega j, and so on. You have infinite terms. So, if you look at this is a geometric series. And it converges for a common ratio which is e to the power e to the power minus beta h cut omega j, that is a common ratio. And I know as the summation goes towards larger and larger n, this common ratio will go to 0. So, this series is uniformly convergent for this common ratio, and so I can write down this as product over j going from 1 to 3n e raised to minus beta h cut omega j by 2, and the product has been the geometric series has been reduced to this sum, which is 1 upon 1 minus the common ratio, which is e raised to minus beta h cut omega j. So, this is equal to the sum 1 upon 1 minus, okay. So, this is common ratio, fine. So, now you can see that I can reduce it further by just multiplying the numerator and denominator with e to the power beta h cut omega j. So, this will give me 1 upon e to the power beta h cut omega j by 2 minus e to the power minus beta h cut omega j by 2, okay. And this can be visualized to be as nothing but product of 3n. I can write it as 1 upon I can write it as twice sine hyperbolic of beta h cut omega j by 2, okay, fine. So, this is nothing but our partition function. So, I can write down my logarithm of the partition function that sort of builds connection with thermodynamics. So, I can write down my ln z as nothing but the logarithm of products becomes a summation of logarithms, and the fact that you have a inverse for each term, it simply gives me a negative sign outside, and it becomes a summation over all the 3n oscillators of logarithm twice sine hyperbolic beta h cut omega j by 2, that is the expression for your partition function for our 3n dimensional solid, okay. So, now you can build thermodynamics from here. So, what you want to do from this onwards is we know that so I am just going to as you take your system to be very large. So, as n goes to infinity and your volume goes to infinity such that your number of particles becomes finite, and you have a well defined homogeneous density. In this limit, you can think of your wave vectors to be tightly spaced in the box, in the sense that any wave vector k that you take for your system would be nothing but a collection of these components of the wave vector, and I can call these components of the wave vector as 2 pi nx over L, 2 pi nx ny over L, assuming you have a cubic box, and what are these nx, ny, nz? Nx, ny, nz are nothing but the excitation of each oscillator that you have taken. So, each oscillator that you said is an excitation of ni. I can actually write down that ni as a combination of nix, niy and niz. So, the Nx, Ny, Nz are basically the components of the excitation of any oscillator in the system. So, if you take this L to be very large, then you can think of your wave vectors k to be very closely spaced, because the minimum wave vector that you can have is basically 2 pi by L into Nx, 2 pi by L into Ny and 2 pi by L into Nz. So, if L goes to very large, the delta k, that is the separation between your wave vectors, goes to 0. Okay. Since you can write down the k minimum is nothing but in some sense the you can take Nx, Ny, Nz to be 1, that is the minimum value of so this k minimum would be nothing but 2 pi by L of the order of 2 pi by L. So, it is basically 2 pi by L square plus 2 pi by L square plus 2 pi by L square and the whole thing. So, this would be the minimum. From k minimum you can construct the magnitude of k minimum. So, you know that it would be of the order 2 pi by L, okay, because sum of these 3 is the same order. If we take the square root is of the order 1 by L. So, as L goes to infinity, our separation between the modes goes to 0. Okay. So, you can think of the summation here in 1, it will turn into an integral. Okay. Now, we are, as modes are coming close, since omega is proportional to k, omega is actually c times k, the actual relationship is so if k's are coming very close to each other, we expect omegas to be also very closely. In fact, the c is not the velocity of light, the c is acoustic speed. Okay. Please make the distinction here, my c is the acoustic speed. We are talking about vibrations of in a solid. So, basically we are talking about the speed of sound in the solid. So, c here corresponds to the acoustic speed, and as k becomes tighter and tighter in a system, as we have just seen, we expect the omegas also to be very close and close to each other. Now, if you have large number of these omegas and they are all very close to each other, then it makes no sense to continue with this summation, that is very painful. Okay. So, what you will have in this instead of this is that as n goes to infinity, our upper limit of the summation also go to infinity, and your omegas are very close stacked now. So, I am going to convert this summation into an integral in the thermodynamic limit. Okay. So, in the thermodynamic limit, as modes are more and more and they are tightly spaced, because of the arguments that just preceded, it makes a good it makes good sense if I write down my ln z as an integral. So, I am going to write down my ln z as an integral. So, this would be like 0 to omega will go from 0 to infinity, and I will have to integrate ln of twice sine hyperbolic into beta h cut omega 0 by 2, correct, and there shall not be any in fact just omega. The subscript on omega will not disappear because we are integrating over all omega d omega. Now, as you can see, this integration is not correct unless I take into account a certain density of states, because otherwise this integration is not dimensionally consistent. You see, this quantity g of omega should have the dimensions of 1 over omega, only then this integration is dimensionless and becomes our ln(z). But what should be this g of omega, and why should we have g of omega? Well, the simple reason is we have gone from summation over all omegas to integral over all omegas. Now, this integration only makes sense if you are multiplying your integrand with the density of states. So, in some sense the density of states is required to basically say that your if you have number of states in some frequency interval, okay, then if you integrate over the entire frequency interval, then the summation of overall g of omega is simply unity or number of modes if you have not normalized your density of states. So, this should simply give me all the number of modes in the system, okay, all the modes in the system. Because number of modes per unit energy range, if you integrate over all the range, should give you the total number of modes. Okay. So, depending upon what density of states we choose, we can get different answers, and in this the first case that I am going to take here today is the case proposed by Einstein, who said that all 3n oscillators are oscillating with the same frequency. So, that was the most simple quantum mechanical prescription given by Einstein. He said that let us not worry about, let us say question asked in the beginning was, are all omega j's the same. So, I said that let us start with all omega j's different, but now here we are with a nice expression in the continuum limit. The first solution was given by Einstein, who said that instead of taking all omegas to be different, why not take them all to be the same. So, Einstein proposed Einstein's proposal was to take all oscillators with the same frequency. So, in some sense Einstein was saying that the density of states here is like a Dirac delta distribution. What does this mean? He was saying that all oscillators having the same frequencies. Now, if you ask question what is the number of oscillators per frequency, this has to be infinity, because its frequency width is 0, everything is in one frequency, okay, and you got n or 3n oscillators, all of them oscillating with omega 0, which means if you consider dn by d omega, it has got to be infinity, because number of oscillators in your unit frequency width, the width is 0, everything is in one oscillator, everything is on one frequency. So, this has got to be a Dirac delta distribution. So, you can think of these omega here as the Einstein's frequency. Omega 0 is the frequency of all the oscillators. It is like saying that so if each oscillator's frequency is same and you ask me what is the density of states, it has got to be a delta function, okay, because if you integrate this over all the frequency space, then there has got to be simply 1, it has got to be simply if you take it as n times 3n times delta. So, then this simply gives me the number of oscillators. Okay. So, we are going to take this example of the Einstein's oscillator, Einstein's model, and proceed with the calculation. Okay. So, I am going to take the example of the Einstein's model and compute the partition function. So, So, the question is what is the heat capacity in this model. Okay. So, let us first compute the partition function, because from there we compute all the quantities. So, our partition function is basically ln z, or logarithm of the partition function has been already computed to be negative of the derivative of g omega, which is 3n times this Dirac delta distribution into the logarithm of 2 sine hyperbolic beta h cut omega 0 by 2 just omega, of course, d omega, correct. Now, you can see that the by the property of delta function, the delta distribution, the entire integral picks up the contribution from the function where the delta function has its source. So, the source is at omega 0. So, the entire integrand comes from that source. So, it is becoming ln of twice sine hyperbolic beta h cut omega 0 by 2. Okay. Now, which means that I can compute the thermodynamic quantities, because this is my bridge that connects StatMech to thermodynamics. So, computing total internal energy, which is nothing but the expectation value of the Hamiltonian, is now cakewalk. So, this is nothing but what we have seen in the last chapter is negative derivative of logarithm z. Okay. If you recall the results of the canonical ensemble, and this is the ensemble in constant NVT conditions, the number of particles, temperature and the volume of the solid does not change. So, this is the canonical partition function, and whose derivative in this form gives you the internal energy. So, negative ln z is already given to me. So, I am just going to copy the previous expression and write this as thrice n, and the derivation of logarithm is just going to give me tangent, not tangent, it is going to give me cot hyperbolic beta h cut omega 0 by 2 into h cut omega 0 by 2. Okay. And I can now write it as 3n h cut omega 0 by 2 into cot hyperbolic beta h cut omega 0 by 2. Right. But this is my total energy. I want heat capacity. Okay. So, the heat capacity at constant volume is given as the temperature derivative of the total energy at constant number of particles and volume. We are in NVT ensemble. So, I am going to write it as 3n h cut omega 0 by 2 into d by dt of cot hyperbolic beta h cut omega 0 by 2. Let us do it carefully. It is natural to do this derivative in terms of beta. Okay. So, what I am going to do here is basically note that so noting that d by d beta can be transformed into a temperature derivative, okay, which means my temperature derivative can be written as minus 1 upon kT square d by d beta, and that would be nothing but minus beta square kb into d by d beta, because beta itself is kT. So, 1 k will cancel, right. So, I am going to substitute this change of derivatives. So, my heat capacity at constant volume will become 3 by 2 into n h cut omega 0, and I get a minus beta square kb into d by d beta of cot hyperbolic beta h cut omega 0 by 2, and let me make some more substitutions. So, I am going to write it as so beta square kb can be written as 1 by kbt, and I will have a 1 kb with a negative sign. No, just a second. So, I am going to write it as yeah, so that would be correct. So, this will be kbt square. Okay. So, beta is 1 upon kT. So, beta square is k square t square in the denominator. So, then I should yeah. So, I am going to write it as just with a minus sign here, and what I am going to do next is multiply and divide by h cut omega 0 by 2. Okay. And then write this as minus 3 by 2 into n kb into, so in fact I am going to write it as minus 3 by 4, because there is there are 2 factors of 2 there, into h cut omega 0 by kbt the whole square, okay, into d by d of h cut omega 0 by in fact I can take the 2 inside here, okay. Fine. So, I can substitute for h cut omega 0 beta by 2 as x. So, this becomes nothing but minus 3 n k b into x square. So, these are substitutions which I believe will make life easy for us. Del by del x square, del by del x of cot hyperbolic h cot hyperbolic x. So, I think it has already made life easy. Okay. And it is known, I am just going to use the fact that the derivative of cot hyperbolic x is nothing but minus 1 upon sin hyperbolic square x. Okay. It is known. So, you can work it out very simple by simply saying that I will write down my cot hyperbolic x. You just use the simple chain rule as cos hyperbolic x divided by sin hyperbolic x, which is nothing but do this derivative up by yourself. So, it would be e to the power x plus e to the power minus x upon e to the power x minus e to the power minus x. So, this is cot hyperbolic x. Do this derivative, you will get minus 1 upon sin hyperbolic x square. Anyway, I am not going to do that derivative here. So, I am going to just write down my internal energy as minus 3 n k b. Yeah, this is heat capacity, I am sorry, it is already taken derivative. It's minus 3 n k b into x square and into minus 1 by sin x square. So, minus turns into positive now. Sin hyperbolic square x. Okay. So, this is nothing but this is 3 times n k b into x square. Okay. So, you can write it as sin hyperbolic square x would be nothing but 1 upon e to the power x minus e to the power minus x by 2 the whole square. So, there will be a 4 in the numerator. Okay. So, this will be, if I call this as, this is becomes 12 times n k b into x square, and I am simply going to take one e raised to minus 6 from the denominator. So, this becomes e raised to x upon so, this becomes, if I so, let me just yeah. So, let me just so, I am going to write down 1 upon, I will take e raised to x by 2. So, that will be e raised to minus 6 and so, I am going to take e raised to x outside. So, this becomes 1 sorry, e raised to minus x outside. So, this becomes correct. Right. So, if I write under the square root under the square, then it simply becomes e raised to x minus e raised to minus x. Okay. So, if you want to understand this, you can say that I am going to write it without the square here. Okay. And then this is the overall square. Okay. Then this goes inside, becomes e raised to x minus e raised to x, and the entire square is outside. So, now I am saying that I want to write it as e raised to minus, if I okay. So, this simply becomes twice n k b into x square e raised to 2 x over e raised to 2 x minus 1 the whole square, and substituting for x, as h cut omega 0 beta by 2, I can write down my heat capacity as thrice in kb h cut omega 0 by kbt whole square e raised to h cut omega 0 beta divided by e raised to h cut omega 0 beta minus 1 the whole square. Fine. So, this tells you something about heat capacity, and that is a very important message here. So, if you try to sketch the heat capacity, you know what is going on. Well, there is one thing definitely, that there is a high temperature limit and there is a low temperature limit. So, at t tending to infinity, that is tending to infinity, your beta will go to 0, because beta is 1 over kT. So, the limit beta tending to infinity, beta tending to 0 is very clear. So, the denominator here becomes it can be very easily seen. So, if your beta goes to 0, then I can write down my I will write down, let me write down everything. So, there is h cut omega 0 beta, right. Okay. So, I have got an h cut omega 0 beta the whole square, okay, which is this term, h cut omega 0 beta the whole square into e raised to h cut omega 0 beta, and I have division by e raised to h cut omega 0 beta minus 1 the whole square. So, this will, if you look at the denominator, this is 1 plus h cut omega 0 beta plus order beta square, okay, then minus 1. So, I am going to drop this to 0. So, this 1 cancels off, and what you have is just denominator is going as h cut omega beta the whole square, and you got a numerator h cut omega 0 beta the whole square, okay, and you got h cut omega 0 beta. So, this will knock off with this, and as the beta goes to 0, this will go as 1. Okay, now the prefactor here is just 3 by 2 nkb. So, the high temperature limit or beta going to 0 limit is just 3 by 2 just 3 nkb. Okay, so this is the high temperature limit, also called the Dulong-Petit law. So, that is the high temperature limit. So, becomes constant at high T heat capacity becomes 3 nkb. Okay. Now, what happens to low temperature? So, this is the high temperature limit. At low temperatures, with this when T going to 0 or beta tending to infinity, in this limit if you look at this expression, so as beta goes to infinity you see that the denominator here, so I am going to just use the same thing. So, just copy it. So, as beta goes to infinity, so I can say that my denominator here becomes so large that I am going to drop 1. So, it goes as h cut omega 0 beta square e raised to h cut omega 0 beta divided by e raised to twice h cut omega 0 beta, because beta is infinity. So, I can drop 1, and so the square becomes twice. Now, this will go as h cut omega 0 beta square into e raised to minus h cut omega 0 beta, and this I will argue that it goes as e raised to minus h cut omega 0 beta as t goes to 0 or beta goes to infinity, for the simple reason being beta square e raised to minus h cut beta will go as e raised to minus h cut beta by L'Hopital's rule. So, you can see my function is basically I can drop h cut omega. So, just raise beta square over e raised to h cut omega 0 beta. So, it is low temp beta infinity limit okay, would simply be the beta infinity limit here and this becomes infinity by infinity. So, you invoke L'Hopital's rule okay, and so what you get here is nothing but if you invoke it twice. So, it gives you just 2 by h cut omega 0 the whole square e raised to beta h cut omega, and that will go to 0 exponentially. So, its low temperature behavior is exponential and high temperature limit is getting to the Dulong-Petit law or saturation. So, here it will go as e raised to minus beta h cut omega 0 okay, and high temperature limit becomes a constant. So, in reality what is basically obtained is a decay to 0 which is much slower than the exponential decay. So, in reality heat capacity is seen to be third power of temperature at low temperatures. So, this is called as in some sense the T cube law, which is universally shown by most metals, and while Einstein's law is fairly accurate at overall temperature region, it does not show a T cube universality at low temperatures. And so, in the next class I will show why this T cube universality cannot be recovered in Einstein's law and what one has to do in order to recover this T cube universality. In this class we stop here, and when we meet again tomorrow we will talk about corrections to Einstein's law, which goes by the name of Debye's corrections. So, Debye proposed some corrections in terms of the density of states of these lattice oscillators to recover the T cube behavior of heat capacity at low temperatures. So, we meet again in the next class and take it up from there. Thank you.